Welcome to the deep dive. Today we're going to be looking at something pretty amazing, patterns in nature. We're going to be going through excerpts from the Wikipedia article, Patterns in Nature. And let me tell you, after this, you're never going to look at a leaf or a seashell quite the same way again.
Yeah, it's really remarkable how these patterns, something we see every day, can reveal so much about how the universe works.
I know, it's like nature has its own language. Like it's
Hmm.
speaking to us through math and science. I was reading how, even those ancient Greek philosophers, they were kind of obsessed with patterns in nature. They saw them as like proof of some kind of, I don't know, like a cosmic order.
And it's fascinating how that idea that there's this order, it's continued to influence scientific thought really throughout history, like from Pythagoras with his harmony of numbers to Leonardo da Vinci with his observations of tree branching patterns. You see this constant search to understand those principles behind nature's designs.
So it wasn't just about pretty shapes for those guys, right? They were trying to understand like the actual building blocks of reality. But I'm curious, did they actually make any like real breakthroughs back then, given how limited their tools were?
Well, they did lay the groundwork for some amazing discoveries. Take Empedocles, for instance. His ideas about how organisms develop, even though they weren't completely accurate, well, they actually kind of foreshadowed parts of Darwin's theory of evolution, which came, what, like centuries later.
Whoa, really?
Mhm.
That's pretty incredible. It's like they were, I don't know, planting seeds of knowledge that, well, that grew generations later. And speaking of growing, I've always been fascinated by the Fibonacci sequence and how it just seems to pop up everywhere in nature. Was that something that, like, those early thinkers were aware of at all?
The Fibonacci sequence, as well as we know it, it wasn't really a thing in the West until the 13th century. But later thinkers like Johannes Kepler, he made that connection between the mathematical sequence and all these natural phenomena, like the arrangement of petals in a flower. Like nature is using a mathematical code to, I don't know, to build its most beautiful creations.
Okay, so we've got those ancient philosophers laying the foundation, then folks like Da Vinci coming along with those sharp observations. But how did we go from there to the actual scientific understanding we have today?
Well, that journey involved, well, a lot of really bright minds, basically trying to put the pieces of the puzzle together. Like in the 19th century, there was Joseph Plateau and his work with soap films, and those were into the secrets of minimal surfaces, the shapes that use the least amount of material for their volume. And it turns out, well, nature loves efficiency, and you see those minimal surfaces everywhere in soap bubbles and even in the structures of cells.
Wow, I never thought of soap bubbles as being mathematically significant. And of course, there's Ernst Haeckel, right? Those incredible drawings he did of marine organisms, they really captured the beauty and symmetry of, well, of the natural world.
Haeckel's work was groundbreaking. I mean, not just because of how beautiful it was, but also because it helped us understand just how much symmetry is present in the natural world. He was one of those rare people who could blend science and art.
I love that. The idea of nature as, I don't know, like a scientist and an artist at the same time, it makes me want to, like, grab my sketchbook and head to the park. But before we do that, let's get back to the science for a minute. We've talked about how patterns are everywhere, but, like, why? What actually causes them?
Well, the causes, they're kind of multi-layered, like a cake with all those delicious layers. You've got mathematics providing those frameworks like chaos theory, fractals, logarithmic spirals. Those are like the recipes for patterns.
So math is like the language that nature uses for its cookbook. That's a great analogy. But it can't be just equations, right? How do those concepts get translated into the real world?
Well, that's where physics enters the picture. It takes those mathematical, I guess you could say, recipes and applies them to the real world. Explains things like why rivers meander, how sand dunes form, even why a soap bubble is spherical. It's about forces, energy, and those laws that govern the physical world.
Okay, so we've got math as the blueprint and physics as the construction crew.
Hmm.
There's got to be more to it, especially when we think about, like, all the patterns we see in living things.
You're exactly right. That's where biology comes in. Specifically in natural selection. Natural selection is like the editor shaping and refining those patterns for survival and for reproduction.
So it's not just about looking good. It's about, I don't know, surviving and passing on your genes, right? It's like survival of the fittest pattern.
Exactly. Take camouflage, for example. Think about a leopard's spots or a butterfly's wings, those that look like a leaf. Those patterns exist because they actually help them to survive, to blend in, and well, to avoid becoming someone's dinner.
Makes sense. But what about the bright, flashy patterns? Surely those aren't about blending in, right?
And those often come down to sexual selection. Think about like a peacock's tail or, the colorful feathers on a male bird. Those are all about attracting mates and, well, signaling that you've got good genes, like saying, hey, look at me.
So it's about more than just avoiding predators. It's also about attracting partners. Nature's a pretty clever matchmaker. So we've got all these forces, math, physics, biology, they all work together to create this amazing tapestry of patterns. But where do we even begin to, categorize all the different types of patterns out there?
That's a great question. I think a good place to start might be with symmetry. It's something we all kind of intuitively find pleasing to look at, and there are actually some really interesting reasons why it's so common in nature.
Symmetry. Okay, that's a great place to start. I think we're going to uncover some really fascinating insights into the world of natural patterns.
Oh, absolutely. Get ready to see symmetry in a whole new light.
Okay, symmetry, it's everywhere,
Mm.
right? Like on a butterfly's wings or a snowflake. But there's got to be more to it than just, you know, looking pretty.
Right, you are. Symmetry in nature, a lot of times, it's about survival, about being efficient. Like a sea anemone, they have that radial symmetry,
Oh, yeah.
which makes sense because they're stuck in one place.
Right.
They got to be able to deal with their environment from all sides.
Yeah, like having a 360-degree view. But what about, like, animals that move around? Their symmetry is different, isn't it?
Exactly. Yeah, animals that move, they usually have bilateral symmetry,
Right.
a left and a right side. That body plan, it lets them move smoothly and it lets them develop those specialized sensory organs up front so they can, get around and interact with their environment.
So it's like having a head and a tail gives you direction, right?
Yeah.
Which you need if you're moving through the world.
Yeah.
But what about snowflakes? I mean, they're not exactly running around, but they have that, six-fold symmetry. What's up with that?
Snowflakes, they're so cool. They show how conditions in the environment can affect patterns. Like as a snowflake forms, it experiences all these changes in temperature and humidity as it falls.
Right.
And those changes create those unique growth patterns on each of its six arms, which gives you that six-fold symmetry. Like each snowflake has its own story about, its journey from the sky.
I love that. Each snowflake, a tiny little masterpiece. We talked about math being nature's language earlier, and when I think math and patterns, I immediately think about fractals. That self-similarity thing, it just blows my mind. It's like nature uses these building blocks and it repeats them at different sizes to make these crazy complex structures.
And those fractal-like structures, they're not just pretty, they're functional too. Take a tree, for instance. That branching pattern, it's a classic example of a fractal. It helps the tree distribute nutrients efficiently, and get the most sunlight.
It's not just about looking good, it's about function too. And fractals, they're not just in trees, right? I remember reading that they're in like all kinds of unexpected places.
Oh, yeah, absolutely. You see those fractal patterns in coastlines, in clouds, rivers, even in our own bodies, like in our lungs and circulatory systems. All those branches, they make it possible to transport things efficiently over a large area, whether it's, air, nutrients, or blood.
Wow, it's amazing to think that the same pattern that makes a coastline so beautiful is also inside us. And speaking of beautiful designs in nature, we can't forget about spirals. They're everywhere. From, seashells to galaxies. It's like a universal design element.
Spirals are definitely captivating. They show how growth and movement often go along, like the path of least resistance. And that creates those really elegant spiraling forms, like a nautilus shell. That's a classic logarithmic spiral. As the nautilus grows, it adds these chambers to its shell, and each one is, a little bit bigger than the last one, creating that spiral shape.
And the Fibonacci sequence, that math thing we talked about earlier, that appears in those spirals too, right? Like there's a secret math code guiding the growth of those organisms.
Yeah, exactly. The way leaves are arranged on a stem or seeds in a sunflower, the spiral of a nautilus shell, they often show those Fibonacci ratios. And that arrangement, it helps things be packed efficiently, make sure everything has enough space and gets enough resources like sunlight.
It's like nature's this master architect using math to create designs that are both efficient and beautiful. But nature isn't always, perfectly ordered, is it? Like it can be pretty chaotic too, right? Think about the weather or the ocean or, I don't know, how cracks just randomly form in a rock.
You're right. Chaos is, well, it's definitely a big part of nature, and it's actually closely tied to those fractals we were talking about.
Really? How so? I don't get how chaos and fractals are connected.
So chaotic systems, the ones that are really sensitive to those initial conditions, they often show fractal behavior. A tiny change at the start can lead to like totally different results, but the system still creates these patterns with that fractal structure. Think of a coastline, it's always being changed by these chaotic forces, waves, erosion, but the shape overall often looks like a fractal.
So even when things seem random, there's still an order to them. That's kind of mind-blowing.
Exactly. And one of the coolest examples of that is something called a vortex street. Have you ever seen those, swirling cloud patterns behind an island or a mountain?
Oh, yeah. I actually saw some pictures online recently. They're beautiful, like brushstrokes on a canvas.
Those patterns are created by how airflow separates when it goes over something. The air makes these swirls, these vortices, and creates those organized patterns, even though it's a chaotic system. It shows that even when things seem random, there are forces at work shaping the world around us.
It's like nature's playing cosmic billiards with these unseen forces guiding everything from, air to ocean currents. And speaking of waves, those are a great example of patterns in motion, aren't they? I love watching them crash on the shore. What kind of patterns do waves make?
So when waves go through water, they transfer energy, and that energy creates those ripple patterns you see on beaches. And those ripples, they're not just pretty, they help shape the coastlines and, impact marine ecosystems.
And those ripples, they can eventually become like full-on sand dunes, right? I've seen pictures of deserts, just vast landscapes shaped by the wind. It's amazing that wind blowing over sand can make so many different patterns.
You're right. When wind blows over all that sand, it can create so many dune patterns. You get crescents, lines, stars, domes, parabolas, even these sword shapes. It's like nature is an artist sculpting the landscape.
Wow, that's a lot of shapes. Which one's your favorite?
I find Barchan dunes really interesting. They're crescent-shaped with their points facing downwind, and they form from this balance of wind, sand movement, and gravity.
Oh, yeah, I've seen pictures.
So the wind pushes the sand up the, gentler slope, and as it gets to the top, it falls down that steep face, creating that crescent.
So it's like a dance between all those forces. Is there anything special about how those dunes form?
What's cool about Barchan dunes is that they're always moving, always changing. The way the sand falls down that steep face, it's a non-linear process, so like small changes can have big effects. You can add sand to the dunes slowly and nothing happens, but then one grain of sand can cause a huge avalanche, changing the dune in a second.
Whoa, really?
Yeah.
It's like a reminder that even, simple systems can be super complex. Sand dunes aren't just piles of sand. They're like systems always responding to the environment.
Exactly. They're a great example of how patterns in nature, they're often a reflection of dynamic processes, not just static shapes.
All right, from the vastness of deserts, let's zoom into something a bit more delicate, like bubbles and foam. What can we learn about patterns from, I don't know, from soap bubbles?
Bubbles are a fantastic way to show minimal surfaces.
Yeah.
Those shapes that use the least amount of surface area to enclose a certain volume. A single soap bubble, it makes a perfect sphere because that's the best way to hold that amount of air.
Right.
But when you get a bunch of bubbles together, that's when it gets really interesting.
Yeah, you get those weird shapes, almost geometric, when they clump together.
Those shapes, they follow something called Plateau's laws, which tell you the angles that soap films meet at. Those laws create this balance of forces, and that leads to those cool geometric patterns. And you know what? Nature actually uses those same rules to build some pretty awesome structures.
Wait, so the patterns in soap bubbles, we see those in nature too. Tell me more.
Yeah. We see those bubble-like patterns in some pretty surprising places, like the skeletons of radiolarians. Those are tiny marine creatures, and their skeletons often look like mineral versions of soap bubbles.
Mhm.
And some sponges and sea urchins, they also have those intricate structures that look like foam. It just goes to show that the same principles can work at totally different scales, from the microscopic to the huge.
It seems like nature really loves geometry, using these basic rules to create structures that are beautiful and, functional. Speaking of geometry, our next stop is tessellations. Those repeating patterns that cover a surface without any gaps. They're like figurative artists and mathematicians, but do they show up in nature?
Well, perfect tessellations, you see those more in, man-made designs, but nature has some pretty awesome examples.
Okay, so where can we find those tessellations in nature?
One really cool one is a honeycomb. Those hexagonal cells, they fit together perfectly, using the least amount of material to make the most space.
It's like the ultimate inefficient design.
Right. We also see tessellations in fish scales, the plates on a turtle's shell, even in the arrangement of petals on certain flowers, like the snake's head fritillary. And of course, the arrangement of atoms in a crystal. That's a classic 3D tessellation. Nature uses these patterns on like every level.
From the neatness of tessellations, let's go to something a little less predictable, like cracks. I mean, they seem kind of random, but I bet there's more to them than we think.
You're right. Cracks, those openings that, help relieve stress in a material, they can actually tell us a lot about that material.
Cracks, yeah, those things that, form in materials. What can they tell us?
Well, the pattern of the cracks, it can show you if something is elastic or inelastic.
Okay.
So when an elastic material cracks, you get those 120-degree joints, where three cracks meet. But inelastic materials, they usually form straight cracks.
So the way something breaks can tell you about, like, what it's made of.
Yeah.
That's pretty neat. What about tree bark? Those patterns, are they cracks too?
Tree bark, yeah, that's a great example of how what a material is made of affects its crack patterns.
Yeah.
Bark is, tough, fibrous, and that makes the cracks grow in specific ways.
Right.
And each tree species has its own unique pattern, almost like, I don't know, a fingerprint.
I never thought about it that way. It's like a secret code on each tree.
Exactly. And that brings us to, I think, one of the most visually striking patterns in nature, one that people have always been fascinated by, spots and stripes.
Oh, yeah. Spots and stripes. It's like nature's way of, dressing up the animal kingdom. I mean, from leopards and zebras to ladybugs, those patterns are, like, super eye-catching. But I'm guessing they're not just for looks, are they?
You got it. Those
Yeah.
spots and stripes, they're all about survival.
Yeah.
They're there for a reason. One of the most common reasons is camouflage. Like a leopard spots, they help it blend into, the shadows in the forest.
So it's like wearing nature's camo.
Exactly. And then there are patterns that are, they're warnings, like the bright colors on a ladybug, that tells predators it's toxic.
Yeah, don't eat me. But how do those patterns actually form? Is it like a genetic blueprint for spots and stripes?
One of the key mechanisms is something called a reaction diffusion system.
Okay.
It was proposed by Alan Turing. Remember that mathematician we talked about earlier?
Wait, the same guy who, like, cracked the Enigma code also figured out how animal patterns work?
Your Turing was brilliant. He thought that these patterns, they could be from chemicals interacting. These chemicals are called morphogens, and they either, activate or inhibit the production of pigments in cells.
Oh, okay.
As these chemicals spread, they can create those intricate patterns of spots and stripes.
So it's like a chemical dance happening on the animal's skin or fur.
Yeah, like imagine a drop of ink in water. You see those swirling patterns. It's similar with these systems. The morphogens spread, they interact, and they create the spots and stripes. And the variations you see, the size, the shape of the spots, the width of the stripes, that all depends on things like the concentration of the morphogens, how fast they spread, things like that.
It's not just random. It's like a chemical ballet. It's crazy to think that such simple interactions can make so many different patterns.
And research is still going on, discovering new things. Richard Prum, he's an evolutionary biologist. He's come up with models that explain, like, the patterns we see in bird feathers, like the intricate ones on guinea fowl.
The deeper we go, the more complex it gets.
Yeah.
But even with everything we know, are there still mysteries about these patterns?
Absolutely, yeah. We've talked about a lot, but there's always more to find out. Like, there are patterns formed by plants, like the stripes of tiger bush in a desert. Those are from, not enough water. Or those waves in conifer forests, those are from wind and regrowth patterns.
So even the way plants grow can create these huge patterns.
Yeah, and there are others that we're still trying to figure out, like Mima mounds. Those are like domes and grasslands.
Okay.
And fairy circles, those bare patches in deserts. We think animals are involved, but we're not sure how.
So even today, there are still these mysteries about patterns. It makes me want to go out and start looking for them myself.
That's what's so great about patterns. They make us want to look closer, to ask questions, to, be amazed by the world around us.
Well, I don't know about you, but I'm, like, totally mind blown. I'm going to be seeing the world in a whole new way after this.
Oh.
From the cracks in the sidewalk to, like, the spiral of a galaxy, I'll be looking for those hidden patterns, those codes that reveal the beauty of nature.
And maybe that's the most important thing to take away from all this.
Yeah.
How everything is connected. From the tiniest atom to the whole universe, patterns show us the order, the beauty of it all. And we're all a part of that.
So to everyone listening, I want you to take a minute today to really look at the patterns you see. Think about what causes them, the history behind them, the connections they reveal. You might be surprised by what you find.
And remember, there's always more to learn. So keep exploring, keep asking questions, keep looking for those hidden patterns that connect us all.